Okay, today we're going to be looking at the elastic potential energy worksheet, and first and foremost, there was a glitch in the program, so for some strange reason there's two copies of this page, so just skip the first one and go right to the second one. Now, quick reminder, elastic potential energy is energy that is stored inside a spring due to the work done in compressing it or stretching it. Okay, and we can find the potential energy elastic formula by doing 1/2 Kx². Okay, and this still comes from work because the elastic is still the work done, is work done on the object. So it's the force times the displacement, but it's got to be the average force, and that's where the 1/2 comes. So the first one we're going to look at is example 1. What is the elastic potential energy of a car spring that's been stretched 0.5 meters? Spring constant for the car is 90 newtons per meter. Okay, so again, we'll go with our guess. So we know how far it's been stretched, and how far it's been stretched is labeled by X. So that's going to be 0.5 meters. And then our spring constant is going to be 90 newtons per meter. And so potential energy stored in the spring, which we'll call PE sub S, is equal to 1/2 Kx². So we'll do the potential energy stored in the spring is equal to 1/2 of the 90 newtons per meter, and then we'll multiply that by 0.5 meters, but don't forget to square it. And when we do that, we'll end up with 11.25 joules. Example number 2, here they don't give us how far it's been, or how the spring constant, so we have to go find it. So for that, we're going to go back to Hooke's law. Hooke's law states that the force exerted on a spring is equal to the spring constant times the amount of compression or expansion. So in this case, they give us the force, and I'll write this down. So givens, we'll change back to red. The force applied is 20 newtons. And we know the amount of compression, in this case, or how far it's been stretched from equilibrium or compressed, is 0.08 meters. And so we're going to do Hooke's law. So we know the force, 20 newtons. Spring constant, that's what we're looking for. And so our X, that's how it's been stretched, 0.08. So on that one, that's going to give us, meters. When we solve for that, that K is now going to be 250 newtons per meter. We know it's newtons per meter because we took the 20 newtons and we divided by the 0.08. In part B, they want us to find the elastic potential energy. So for that one, I'll change this back to green. And for that, potential energy stored in the spring, 1/2 Kx². And for that, 1/2 of the 250 newtons per meter times 0.08 meters, but don't forget to square it. And when we do that, that's going to give us a whopping 0.8 joules. Okay. The other way that we can do this too, quick reminder, and I'll just put this in there, we can always say that the work done is equal to the average force times the displacement as well. In this case, because this force is going to go to 20 newtons, okay, the average force is going to go between 0 and 20, so my average force is actually going to be 10 newtons. And then I can multiply that by how far it stretches or compresses, so that's 0.08 meters, and that's still going to give us the 0.8 joules, or newton meters. All right, then we look at example number 3, another work it out one. We've got a spring of the force constant, so I'll put this down, go to the maroon here. So my K is equal to 5.2 newtons per meter, and it has a relaxed length. So the original X initial is 2.45 meters. After we attach a mass to it, my X final is going to be 3.57 meters. We want to calculate the elastic potential energy. Okay, so for this one, potential energy stored in the spring, we'll stick maroon. Potential energy stored in the spring is equal to 1/2 Kx². But you got to remember, this X is how far it's been stretched. So the first thing we have to do is that we have to subtract these two in order to find out what our X is. And so when I do that, I find that my X, my delta X, if you will, is going to be 1.12 meters. So once I get that, I can do my potential energy stored in the spring is equal to 1/2 of the 5.2 newtons per meter times the 1.12 meters. Don't forget to square it. And when we get that, we get 3.26 joules. Okay, now for the rest of these, we've got 9 multiple choice questions, and we'll just go through these. What type of potential energy results from bending, stretching, and compressing matter? And that is going to be elastic. Okay, you have chemical potential energy. That's energy that's stored in a substance when you burn or release it through a chemical reaction. Gravitational potential energy, that's the other one that we talked about, where the energy is stored in by how far it is lifted off of the ground. And then nuclear energy, we'll talk about that when we get into modern physics. A spring having a spring constant of 180 newtons per meter, is stretched 0.51 from its equilibrium. How much elastic potential energy does the spring possess? So we go potential energy stored in the spring is equal to 1/2 k x squared. And so we'd say 1/2 of the 180 newtons per meter. And we're going to multiply that by the 0.51 meters. Don't forget to square it. And when we do that, we're going to end up with about 23 joules. So it's going to be choice B. Number 3, horizontal spring with a spring constant of 140 newtons per meter is extended 0.2 meters from the equilibrium. How much elastic potential energy? So again, potential energy stored in the spring, 1/2 kx squared. In this case, our k is the 140 newtons per meter. My x is 0.2 meters. Don't forget to square it. And when you do that, you're going to end up with roughly 2.8 joules. So choice A. Number 4, what's the elastic potential energy stored in a spring of spring constant of 3.5 newtons per meter, extended by 0.85. So again, this is getting kind of old, but we'll keep going on it. Potential energy stored in the spring, 1/2 kx squared. So we've got 1/2 of now the 3.5 newtons per meter. And now we're going to multiply that by 0.85 meters. But don't forget to square it. And when we do that, we're going to get 1.3 joules. So again, choice A. Number 5, which of the following is an example of the object with elastic potential energy? Wind up towards combined bond up. Yeah, that sounds pretty good, actually. Compressed basketball. Oh yeah, well if you compress it, then you're storing it by compressing that down, that elastic thing, stretch rubber band. So I gotta go with choice D. It is definitely all the above. So looking at number 6, we've got a 4 kilogram block is attached to a vertical spring constant of 800 newtons per meter. The spring stretches 5 centimeters down. How much elastic potential energy is stored in the system? Now there is a little glitch here, and I'm going to focus in on it. It says it's 5 centimeters. Remember, we live in an MKS world, so we got to make sure we change this over. So this is going to become 5 times 10 to the negative second meters. Okay, we know the spring constant. That's 800 newtons per meter. We know how far it's been stretched, so this is going to be delta x. So again, we do our potential energy stored in the spring, 1/2 k x squared. So potential energy stored in the spring was 1/2 of my 800 newtons per meter. And then I'm going to multiply that by my 5 times 10 to the negative second meters. But again, don't forget to square it. So when I do this, I'm going to get roughly 1 joule.
Nice.
My wife talking to the dog. Number 7, a heavy block suspended vertical spring. Elastic potential stored in the spring is 2 joules. But the spring constant of the elongation is 10 centimeters. Again, I'm worried here. I've got that 10 centimeters. I got to immediately change that over. So this is going to be 10 times 10 to the negative second meters. Or you could put it as 0.1. That also works. Yep. And we know the potential energy. So potential energy stored in the spring is 1/2 kx squared. So now potential energy stored in the spring is going to be 2 joules. 1/2, we're looking for the spring constant, and we know that our x is going to be 10 times 10 to the negative second meters. Don't forget to square it. Remember, we have to be in meters in order to do this. If our energy is in joules, we have to be in meters. And so for this one, we're going to find, when we solve this out, we should get right around 400 newtons per meter. So K is equal to 400 newtons per meter. So choice A. And number 8, a heavy block is suspended from a vertical spring. Elastic potential stored in the spring is 0.8 joules. What's the elongation? The spring constant is 100 newtons per meter. So here we can go, all right, we've got potential energy is 0.8 joules is my PE. I know that my spring constant K is 100 newtons per meter. And I'm looking for delta X. We're looking for X. How far did it stretch? So again, same equation. Potential energy spring, 1/2 kx squared. So I've got 0.8 joules is equal to 1/2 of 100 newtons per meter. And that's going to then times X squared. So we solve through this. We're going to get approximately, X is going to kick out to be about, that doesn't seem right. Let me pause this for a second. I had to check that just to make sure I didn't make a mistake before, but it is equal to 0.126 meters, which is going to get us closest to 113 times 10 to the negative second, or 0.13, so it's got to be choice D. So it's closest to the 13 centimeters. All right, and our last one, an apple is gently hung from a spring that stretches 4.6 centimeters. Okay, so again, we've got that centimeters piece. I'll highlight it just because I bet that's what we've been doing before. So let's change that over. Let's go to green. Let's go to maroon on this one. So we got 4.6 times 10 to the negative second meters. That's my X. And we know the potential energy is equal to 0.056 joules. Okay, and so we're looking for our spring constant, or force constant. Notice they use the term force constant here instead of spring constant. They're interchangeable, it's the same thing. So we're looking for K. So we know our potential energy stored in the spring, 1/2 kx squared. So 0.056 joules is equal to 1/2 of my K, which is what I'm looking for. It's bad K. Try that again. The 4.6 times 10 to the negative second meters. Don't forget to square it. And we're going to get K. It's going to be approximately 53 newtons per meter. So I hope that helps. If you have any continued questions, come see me. All right, everybody have a great night. See you, bye.